So in the last video, I said that functional programming is a programming paradigm that's driven by one key principle that says that all computation is represented by mathematical functions. And we saw that mathematical functions can't change their inputs. So as a result, we have this idea of immutability, where variables can't be changed. And I said that this was more of a trade-off than a detriment, because although we lose some expression in our languages, such as loops and counters, we gain some benefits. And so in this video, I'd like to explore what those benefits are. So the first benefit that I want to outline is the idea that it makes our programs more logical and more predictable. And the second idea that I want to explore is that this idea of immutability makes functional programming perfect or built for distributed computing. And we'll see what that is later. Distributed computing. So the first thing I want to talk about is how immutability makes our programs more logical. So let's say I'm in a new language and I'm using some library with some functions that I don't really understand how they're implemented, but I know they're supposed to do something. Let's call one such function black box, and let's say it takes one argument. And I want to use it in the following program. I want to say, well, I have a variable x and I'm going to set it equal to 5. And I'm going to run the black box function on x. And I want to see if this function is equal to running the black box function again on the same argument. I want to see whether this first running is equal to second running. Well, logically, we would think that the result should be true, right? Why should the result change if I don't change anything? But however, we could also get false. And one reason is in a language like JavaScript, this first black box function could change what x is. It could say x is equal to x plus 1. And then this would mean that when we run the first black box function, it updates x to be 6. And so when the second black box function runs, x has already been updated to 6. And so this says, well, x is equal to x plus 1. And so now x is 7. And so these two numbers aren't the same. And so we get different results. Another possibility to get false is that black box x, at least the first one, changes a global variable that the second one tries to access. And now that it's changed, we get an entirely different result. But even more than just true and false, we can get some different results. But how? I mean, this is a Boolean expression. It should either be true or false. But we could also segfault. And the reason we could segfault is that this first black box function frees some memory that the second black box function tries to access. And the computer goes, wait, you don't have access to this part of memory. So I'm going to stop you right there. I'm going to throw a segfault. So we can see that we can get true, we can get false, and we can also get a series of errors. And this isn't good. I mean, this is a one-line call. And we can get so many different outputs if I don't really understand how black box X functions. But if I were programming functionally, I could say a few things. Well, I could say that, well, our function will never update variables, right? Because that's impossible. We ruled that out when we first introduced functional programming. So we can't get different results that way. And we can't change memory. We can't free memory because in order to do so, we would have to have a function that does that. And functions can't do that because there's no function that gets to update memory. And so as a result, we got to throw out the possibility of getting false or getting any errors. And this means that black box X is always going to be equal to black box X. And that makes a lot of sense. It makes our programs more logical, and it gives us a better way to reason about programs without diving into the source code of every single library that we're looking at. And the second benefit I want to take a look at is the more important benefit, at least for the coming couple of years. It's the idea that because of immutability, functional programming is a programming paradigm that's built for distributed computing. So what exactly is distributed computing? Distributed computing. Well, distributed computing is the idea that we separate computation into lots of small parts that we give to a bunch of different computers to process. And distributed computing has its origins in physical limitations on processors. So I'm going to draw a processor as a box with a circle in it. So processors are the heart of our computers. They're what do all the computation to make our computers run so well. And so we want them to be as fast as possible. But recently we've discovered that trying to speed up processors is either too expensive or too difficult. So what we've resorted to doing is we've said, well, instead of making one processor faster, let's combine these two processors together. I mean, my current computer has 4 processors or 4 cores running at the same time, trying to separate computation and coordinate computation. And so as a result, when I glue these two processors together, I might get an improvement on speed. I can do more computations. But I might not get twice as much computation. I might get only 1.8x the speed. And the reason for this is that these two processors need to be coordinated somehow. The first processor can't redo work that the second processor has done because that's inefficient. And the second processor can't perform any functions that interfere with the first processor because that would throw off all of the computation and we get the wrong answer. So in order to do some of this coordination, we lose some speed. Great, so that's what distributed computing is. Recently, it's been taken to an extreme. We've said that, well, if gluing two processors together is great, why not coordinate thousands, hundreds of thousands of processors together in what's now being called cloud computing, where we take one really large computation and separate it into a bunch of smaller computations that we can send off to various computers and servers across the world and combine the answer at the very end and hopefully speed up that process enough so that we can, perform more computations. But the problem of this is that we need to coordinate all of these processors, which could potentially range from the hundreds to hundreds of thousands of processors. And we need some way to coordinate them well. Well, functional programming and the promise of immutability gives us a great way to do that, because everything in functional programming is represented by functions. And we've said that functions can't interfere with one another because they're immutable and they can't change the state or affect other functions, the execution of other functions. This means that when we have a program, we can immediately, very simply separate the computation, the actual processor work, into several distinct parts that we can say, okay, the first processor gets this computation, the second processor gets this computation, the third processor gets this computation, and at the very end, we're going to combine all the results in some way to get the answer. And functional programming, because its functions are set up to be this disjoint, sort of non-interfering way, we can very easily distribute our computation without writing too much code. It makes functional programming a very good tool to do distributed computing. And this means that functional programming is a tool that many people will want to use as more and more things demand cloud computing or demand distributed computing. Because even though you can do this in other languages, it's just harder to coordinate all of these moving pieces. You have functions that, I don't really know if it interferes with another computation, so therefore I have to delay that computation until this computation is finished on the first core, and therefore only then can the second core start its computation. There's a lot of coordination work that functional programming automatically does for us. This makes functional programming perfect for distributed computing. And so this is why functional programming is extremely practically relevant in the coming years. More and more people will want to use functional programming to do cloud computing. So let's recap what we saw in this video. What are the benefits of trading up counters, trading up loops? Well, we see that the guarantee of immutability makes our programs more logical, where we can say, okay, this function can't interfere with that function, it can't access memory. Great. And that means that it's great for functional programming to be done with distributed computing. We can separate all of our computation, because they're already functions, into separate distinct chunks that we can distribute to hundreds and potentially thousands of processors, and easily do that with functional programming. And that's why functional programming will still be extremely relevant, not only as a mental exercise or a way of becoming a better thinker, but practically as well.